So this is part 5 to the algebra and trig review problems. I figured I would continue where I left off last time, just doing some more trig problems. So for number 10, says solve that 2 sine squared theta plus 3 sine theta plus 1 equals 0, where 0 is less than or equal to theta, less than or equal to 2 pi. And number 11 says solve sine of 5x equal to negative square root of 3. On the interval, actually there needs to be a 2 here. 2 times sine of 5x equal to negative square root of 3 on the interval 0 to 2 pi. All right, so these ones specify an interval in which you're confined for theta. So this means we'll have a specific solution rather than a general solution. So the last video, I did a trig equation and I talked about how there was a general solution and specific solution because there wasn't this specification of an interval. Now they tell us that theta is confined to be between 0 and 2 pi. So any answers I get, they have to be within these bounds. So let's do number 10. So you'd have to recall from like trigonometry class as far as how would you solve something like this? We're going to use a change of variable so that we can apply rules that we know. So use change of variable. And I'm going to treat sine of theta. I'm going to let, I'll just call it x. Let's say x equals sine of theta. That means this equation is going to be turned into 2x squared plus 3x plus 1 equal to 0. So I just replace sine theta with x. So after I find x, I'm going to have to back substitute and find sine of theta. So after get x, need to get theta by applying what sine of theta is. All right, and to do this, I'm going to factor, and by factoring, I use what's called AC method. And so I'm going to do the first number 2 times the last number 1. So 2 times 1 is 2. Find the pair of factors of 2 that add up to the middle number 3. So it's going to be 2 and 1. So I replace 3x with 2x plus 1x. So that's going to make this turn into 2x squared plus 2x, and then plus 1x, and then plus 1 equal to 0. And then I'm going to group the first two terms together. So I'll group 2x squared with 2x, and then I group the last two terms together, 1x and 1. 2x squared and 2x, so that they share 2x in common. I factor that out, that turns this into x plus 1. 1x plus 1 is the same thing as just x plus 1, but I can always factor out a 1. And that gives you the same thing over again, x plus 1. All right, so they share this x plus 1, so you factor that out. All right, so that's going to give me x plus 1 times, and then 2x plus 1 equal to 0. All right, so I have these two factors, which means I have two different cases. So case 1, x plus 1 equal to 0. You solve for x, that's going to give you -1. Case 2, 2x plus 1 equal to 0. So I would subtract 1, so you have 2x equal to -1. Divide by 2, so you get x is equal to -1/2. All right, I'm not done yet, but these are the two values I get for x. Now I need to go back and substitute what I had earlier. So x was sine of theta. So recall, I did a change of variable. I had x equals sine of theta. So changing it back in terms of theta, this is going to say sine of theta is either -1 or sine of theta is -1/2. All right, and that's where I reference the unit circle and see. So if I consider the sine of theta equal to -1 on the unit circle, sine is -1 at the point where it's 3 pi over 2. If you were to go around 3 pi over 2, that gives you the point 0, -1 for the angle theta. All right, because then sine's the y coordinate. So sine of theta equals -1 when theta is 3 pi over 2. All right, that's part of my answer. Now I need to consider the other case when sine is -1/2. Well, I know sine's the y coordinate, so it's going to be the bottom two quadrants as far as where it occurs. And you can reference the unit circle and determine that the two angles are going to be 7 pi over 6 and 11 pi over 6. So this point is -√3 over 2, -1/2. That occurs when theta is 7 pi over 6. All right, and again, so sine is the y coordinate. Oh, yikes. And the other point occurs at 11 pi over 6. So if I go counterclockwise, 11 pi over 6. That's the point √3 over 2, common -1/2. And again, it's got that -1/2 as the y coordinate. So sine of theta equals -1/2 when theta is 7 pi over 6. And then 11 pi over 6. So combining this all together, we have theta equal to 3 pi over 2, 7 pi over 6, and 11 pi over 6. All right, that's combining everything together, so that's going to be the answer. Again, I'm going like really detailed here. You don't have to draw any unit circle or anything like that. Just need to recognize, well, what theta value gives you that particular value, like sine of theta equals -1, that occurs when theta is 3 pi over 2. All right, so I did a change of variable, and I just chose the variable to be x. So that way that turned the equation to 2x squared plus 3x plus 1. And then I did some factoring. And this factoring I did, this is called the AC method. You can use a different factoring technique, or you can use quadratic equation. So doing all this is called the AC method for factoring. You could have used quadratic formula. So based on the AC method, I got these two factors, x plus 1 and 2x plus 1. And then that gave me x being -1 and -1/2. But I had to change my variable back to what it was. In this case, it was theta. So sine of theta is what x is. So sine of theta equals -1, or sine of theta is -1/2. And that's where I broke up each case, found the corresponding angle theta for which each one of these two equations is true. Okay, so that's how I do that one. Now number 11. Let's see, I had 2 sine 5x equal to -square root of 3. And the interval is 0 to 2 pi. So just like the previous question, we're going to have a specific solution. Now there's no double angle identity I can use, but what I'm going to do, first thing is I'm going to divide both sides by 2. So then I have sine of 5x equal to -square root of 3 over 2. And then in trig, it's implied that if you want to do this, you can put parentheses around the 5x. That's what the sine function is being applied to. But there's no trig identity I can use for this 5x portion. At least I don't see one right away. However, if I treat it as just sine of theta equal to -square root of 3 over 2, I can find theta, which then I can find 5x, what x is. All right, so from the unit circle, So where sine is negative, turns into negative square root of 3 over 2. That occurs at 4 pi over 3 and then 5 pi over 3. Okay, so this occurs at 4 pi over 3. This occurs at 5 pi over 3. Now in general, the general solution, so I have 4 pi over 3, and then I can do multiples of that by 2 pi, adding 2 pi to it for the different revolutions. So it'll be plus 2 in pi. And then the other one would be 5 pi over 3. And then counting for infinite revolutions, that's 2 in pi. Now I'm going to relate this back to 5x. All right, so if I went with option, I'll use a different color. Let's say I went with this one first. So for theta equal 4 pi over 3 plus 2 in pi. That happens when sine of theta is negative square root of 3 over 2. So that means when I do 5x, use theta in place of 5x. So here, I would have 5x equal to 4 pi over 3 plus 2 times n pi. Then I need to get x by itself. Multiply both sides by 1/5. So when you multiply both sides by 1/5, you get x equal to 4 pi over 3 times 1/5 gives me 4 pi over 15. Right, because you do 3 times 5 in the denominator. And then you do 1/5 times 2 in pi. That's going to give 2 in pi over 5. All right, that's for the case, for one of the cases. And again, this is the general solution. And n isn't any integer. I'm going to find the general solution for the other case and then make it to where we're talking about the specific case. All right, and I'll use a different color for this next one. And I'll treat it the same as the other one. So in this case, we're doing sine of 5x and equal to negative square root of 3 over 2. I use 5x in place of theta. So that's going to be when 5x is equal to 5 pi over 3 plus 2 in pi. Multiply both sides by 1/5. like before. That changes it to be x equals, and then that'll be 5 pi over 15. So if I do 5 pi over 3 times 1/5, that's 5 pi over 15, which you can reduce this. So it's pi over 3. So that means I'm going to have x equal to pi over 3 plus 2 in pi over 5. All right, and then this is the general solution for the other case. All right, and then we had this one, that case. So combining these two together, so in general, we had sine of, so the first thing we started out with the 2 times sine of 5x equal to negative square root of 3. Now I found the answers for x in the general terms. So this is x equal, so the first one was 4 pi over 15 plus 2 in pi over 5. All right, so I paused the video and I went ahead and wrote what the two general solutions were for each x value, which I did right here, the one in green and the one in purple. So in general, the solutions for 2 times sine of 5x equal to negative square root of 3, I had to be x equals 4 pi over 15 plus 2 in pi over 5, and the other one was pi over 3 plus 2 in pi over 5. Where n is an integer, meaning it can be like a -2, -1, 0, 1, 2, 3, or whatever. Now to bring it down to the particular solution, or the specific solution, so to form right, the specific solution, because our interval in the question was 0 to 2 pi. Well, obviously I know that one of them, or two of them we know is 4 pi over 15, and then pi over 3. Write that better. All right, and that's when you choose n if n were 0. All right, for instance, x would be equal to 4 pi over 15 plus 2 times 0 times pi over 5, and then that collapses because that's 0, which gives you the 4 pi over 15. And the other one would be the pi over 3 when you plug it in. All right, now the thing is, are these the only two? And really, I would just test different values. So if you did a -1, for instance, so that'd be plus 2 times -1 times pi over 5. And I believe this should be negative when you do 4 over 15 minus 2 over 15, or 2 over 5. So this is negative, so it's not in our bounds. Right, the bounds were 0 to 2 pi. And similar, if I do it for the other one, right, because you're doing pi over 3 minus 2 pi over 5, that's going to be negative also. All right, so it doesn't work when n is -1, because that doesn't lie inside our bounds. So it's not going to work for the other negative values for n. And this is just plugging in different integers to see if there's more than just these two solutions within our bounds. Now, if I did n as 1, let's see, so it'd be 4 pi over 15 plus 2 times 1 times pi over 5. And then I have to find out, well, what is this equal to? So this would be x equal to 4 pi over 15. And then plus 2 pi over 5. You can change this. So 4 pi over 15. I would change 2 pi over 5. So it has 15 in the denominator. So you can add the fractions. 5 times 3 is 15. So you do 2 times 3 is 6 pi over 15. 4 plus 6, that's 10 pi over 15. And then you reduce this. So divide by 5 to 10, that gives 2 pi over 3. So this is within our bounds. All right, so that one works out. That means I have another part of my answer. Two pi over 3. So along with these two, I have also 2 pi over 3. Now I need to check for the other one. So that was doing 4 pi over 15. Now for the other one was pi over 3. So I need to check for that one, see what that gives. All right, and I'm going to need the same denominator for these fractions. I convert these so that the same denominator would be 15. If I convert pi over 3 into something over 15, that's going to be 5 pi over 15. Is the same thing as pi over 3? Because I multiplied 3 by 5 to get 15, so I have to do that to the top. Now the other one, fraction, I have to multiply by 3, so which we already know that's going to be 6 pi over 15. 5 plus 6 is 11. That's 11 pi over 15. And that is within our bounds. All right, so that one holds. All right, so that means I have these two also part of my solutions. And so I took care of when n is 0, n is 1, -1. We know negative numbers don't work because those are going to be negative. when you add it to each corresponding value. So it's going to be not within the bounds. It worked for 0. It worked for 1. Now we need to see, does it work for n equals 2? All right, so the first one was 4 pi over 15. So x equals 4 pi over 15 this time, plus instead of 2 times 1 times pi, it's going to be 2 times 2 times pi over 5. So that's 4 pi over 15 plus 4 pi over 5. I need the same denominator, so common denominator is 15. So that changes this one. I multiply 4 pi over 5 top and bottom by 3. So that makes 4 times 3 is 12. So that's 12 pi over 15. And then I add 4 plus 12. All right, and that's going to give me 16 pi over 15. And then is that within our bounds? And yes, it is, right? Because 16 pi over 5 is still less than 2 pi, or 16 pi over 15 is still less than 2 pi. All right, so that one works. 16 pi over 15. And now I have to check it for the other one. So that was doing the case with 4 pi over 15. Now I need to check it for when it pi over 3. All right, change these so they have common denominator. So 15 is the common denominator. So that's going to make this 5 pi over 15. Then that, I'm going to change this to 12 pi over 15. 12 plus 5. So that's 17. And that is within our bounds. So you see there's a good bit of solutions, specific solutions for this problem. Okay, so 17 pi over 15. And you keep doing this process, and I was using n is 1, n is 2, and now I'm doing n is 3. So I'll demonstrate this one. If it works out, I'll write what it becomes when you use n is 4. So when you plug 3 in for n, so that's going to be, so we still have 4 pi over 15 plus. So it'll be 2n pi over 5. It'll be 2 times 3 pi over 5. So it's going to be 4 pi over 15 plus 6 pi over 5. Same denominator I need is 15. So this one, second fraction, multiply that top and bottom by 3. So 6 times 3. So that's going to make that 18. And then I do 18 plus 4. So 22 pi over 15. And yeah, that's within 0 and 2 pi. Okay, so here's a lot of solutions for this one. All right, and now I need to check for the other one when for pi over 3. All right, so that's pi over 3 plus 6 pi over 5. Convert these into fractions with the same denominator. Let's see, so it's going to be 15. So 5 pi over 15 plus, and then we know that's 18 pi over 15. So I do 18 plus 5, so that's going to give me 23 pi over 15, which again we know is within our bounds. All right, so I'll check that one off. Hopefully, I mean, by now it makes sense what I'm doing. I'm just been doing the same process. I'm just using different values for n that I'm plugging into the general solution so I can get all of the solutions for the specific solution. And I'm going to pause the video now and write down what the other ones are and the corresponding values I used for n. All right, so I paused the video and worked out the next one, and it turns out 28 pi over 15, 29 pi over 15, these are the last two. And so all of these is the solution to the problem. The specific solution. Now, if you want to see the work, I'll have to scroll down real quick. So I already demonstrated for 3 how I got those ones. Now when I plugged in 4, this is how I got these two values, 28 pi over 15 and 29 pi over 15. So if you want, you can pause the video right now and write down these steps. But it's pretty much the same. Just keep doing the same as the previous ones, and you'll see that they're both within the bounds. And I went ahead and just showed that if you did the next one, plugged in 5, you get, for the first case, 4 pi over 15, you get 34 pi over 15, which is greater than 2 pi, because 2 pi is the same thing as 30 pi over 15. And the other case is going to be greater than, because pi over 3 is more than 4 pi over 15. So I can go ahead and just say that this whatever it's going to turn out to be, that's going to be greater than 2 pi, since the pi over 3 value is more than 4 pi over 15, which we already know that came out to be 34 pi over 15. So it doesn't work when n is 5. All right, so it does not work. And that's how, now this was just a long problem just because I had to find all of these different specific solutions. And I'll try to summarize. So for these first two, that's when we use 0 for n. This is when we used 1 for n. That was using 2 for n. That was using 3. And that was using 4. So I had to first find the general solution, because from there I can pick the different values for n to plug in so that I can get the answers to be within our certain boundaries between 0 and 2 pi. All right, so I'll try to recap that real quick. I know it was a long problem. All right, so the problem started out with 2 times sine of 5x equal to negative square root of 3. And what I did was, so I divided both sides by 2, so I can get the sine function by itself. There's no trig identity I can use for 5x. So what I did was I looked at it, well, what is sine of theta? When does that equal negative square root of 3 over 2? And I got the two answers on the unit circle to be 4 pi over 3 and 5 pi over 3. But if I were to do general solution of that, rotating it or doing infinite amount of revolutions, that's why I have the 2n pi added to each one of these, where n is an integer. Now I relate it back to the problem where it had 5x, and I basically treated 5x as theta. And well, I got x by itself by multiplying by 1/5. So the first one gives me 4 pi over 15 plus 2n pi over 5. The second one gives me pi over 3 plus 2n pi over 5. So in general, I have these two as my solutions, where n is an integer. Now to tie things together, I need to get specific solutions that are within our bounds of 0 and 2 pi. And all I did was I picked different values for n and plugged it into these, I guess, general solutions. So like when n is 0, that gave me the 4 pi over 15 and pi over 3. When n is -1, that's going to give me some negative number for both of these cases. So since it's negative, that's not within my bounds. So then I didn't even look at any more negative values for n since it didn't work for -1. So then I just used n is 1, got these two, n is 2, got these two, n is 3, and then n is 4. And then once you hit n is 4, that's the biggest n's going to be, because when you plug in 5 for n, you get some 30 pi over 15 for the first one. The other one's going to be bigger than that. And you can kind of tell just because that's 29 pi over 15, and we know 30 pi over 15 is 2 pi, so it just makes sense. Nothing's going to come after this that's going to be within our bounds. All right, so that's it for this part. I will be making one last part to this algebra and trig review. I wanted to do more trig equation problems to help you out for the homework. So this was part 5. I'm going to make a part 6, and the part 6 will deal with exponential and logarithms.